Right now, as you settle in to hear these words, something impossible is happening to 0.87 astronomical units away from Earth. That's 429 million kilometers, if precision matters to you. And in this case, precision is everything. An object that doesn't belong to our solar system, an intruder that was born around a star, whose light has never warmed human skin, has positioned itself in a configuration so rare that astronomers have been preparing for this moment for months. On January 22nd, 2026 at 2:37 p.m. Universal Time, the interstellar visitor designated 3I Atlas achieved a phase angle of 0.16 degrees relative to Earth and the Sun. Let me break that down, because those numbers contain a mystery that might rewrite what we understand about our place in the cosmos. Phase angle. It sounds abstract, technical, bloodless. But you already know what it means because you've seen it every night of your life. Look at the moon when it's a thin crescent, barely visible against the twilight. That's a high phase angle. You're seeing the moon from the side, mostly in shadow with just a sliver catching sunlight. Now picture a full moon, that perfect luminous disk hanging in the night sky. That's a low phase angle close to zero. You, the moon, and the sun are nearly aligned. You're looking at the moon head minus on, fully illuminated with the sun directly behind you. The geometry is simple, the implications are not. When 3I Atlas reached a phase angle of 0.69 degrees 3 days ago, it meant that Earth, this interstellar object, and our sun formed an almost perfectly straight line. We're looking at 3I Atlas with the sun at our backs. The cosmic equivalent of shining a floodlight directly at something and examining what bounces back. This alignment happens maybe once per century for any given interstellar object, if it happens at all. Most of these visitors swing through our solar system on trajectories that never bring them into opposition with Earth. They arrive, they accelerate past the sun, and they vanish back into the dark, observed only from angles that reveal shadows and ambiguity. But not 3I Atlas. For 1 week 168 hours we have a viewing geometry that strips away the shadows. Every grain of dust around this object, every irregularity on its surface, every asymmetry in how it scatters light becomes visible in a way that will never occur again in human history. This is the forensic window. This is when we find out what 3I Atlas actually is. And here's where your spine should start to tingle. 3I Atlas is not behaving like the other interstellar objects we've catalogued, not like 1I, ONUA. That tumbling cigar-shaped mystery that accelerated away from the sun without a visible tail. Not like 2I Borisov, the mundane interstellar comet that acted exactly like the comets native to our own solar system. 3I Atlas has sprouted an anti-tail. You need to understand what that means. Comets have tails, everyone knows this. Dust and gas blown away from the nucleus by solar radiation. Always pointing away from the sun like a windsock. But an anti-tail is different. It's a narrow spike of material that appears to point toward the sun, a geometric illusion created when Earth passes through the plane of a comet's orbit and we see the dust sheet edge minus on. Anti-tails are rare but not unheard of. What makes your skin prickle is the timing. 3I Atlas's anti-tail became visible exactly as the object approached opposition. And it saned directly at Earth. Not 5 degrees off. Not in the general vicinity. Directly at us during the only week when our instruments can perform the kind of high-precision optical forensics that might reveal whether this object is a pristine relic from another star system or something else entirely. Let's stack the coincidences, shall we? Coincidence: when an interstellar object on a hyperbolic trajectory happens to pass through our solar system. Coincidence to that trajectory brings it into near-perfect opposition with Earth and the Sun. Coincidence 3: the opposition occurs at a phase angle of 0.16 degrees, optimal for a phenomenon called opposition surge, which we'll dissect in excruciating detail shortly. Coincidence 4: an anti-tail structure becomes visible during this exact window, aligned with Earth. Coincidence 5: the object is moving at 57 7 kilometers per second relative to the sun. That last number deserves your full attention. 50 minus 7 kilometers per second. That's the speed that ruins simple narratives. If 3I Atlas were artificial, and I'm not saying it is, but if it were, then maintaining stable, structured behavior at that velocity would require a level of engineering precision that challenges our understanding of what's possible. Every course correction, every orientation, every geometric configuration would need to account for relativistic effects and the sheer momentum of something moving at nearly 208 kilometers per hour. Natural objects don't care about precision at high velocity. They tumble, they outgas genetically. They fragment under thermal stress. If 3I Atlas is natural, then 57.7 kns is just a number, the inevitable result of gravitational dynamics in whatever stellar system birthed this object billions of years ago. But if it's not natural, that number becomes a constraint, a challenge, a price paid for whatever function this object serves. And there's more. Observers at 3 separate facilities, Mauna Kea, the European Southern Observatory, and the Atacama Desert, have reported something that shouldn't exist. Symmetric mini-minus jets, 3 of them, spaced approximately 120 degrees apart around the object's nucleus, firing in a pattern that suggests rotational stability rather than chaotic fragmentation. Let me be clear, comets have jets. Comets outgas from active regions on their surfaces as solar heat vaporizes subsurface ices. These jets are asymmetric, driven by the random geology of a dirty snowball that's been frozen for 4 billion years. They flicker on and off. They cluster on the sun-facing hemisphere. They do not arrange themselves in hemisphere. They do not arrange themselves in geometric patterns. But that's what the preliminary data suggests. 3 jets, even spacing, repeatable behavior. The raw images are being processed right now. Teams are checking for artifacts, for optical illusions, for the deconvolution errors that can make a fuzzy blob look like a structured emission. The truth protocol is in effect. If it's real, multiple instruments will see it. Raw data will exist. The pattern will reproduce across different telescopes using different processing workflows. We'll know within days whether those jets are real. And if they are real, we'll need to explain why an object from another star system, hurtling through our cosmic neighborhood at 57.7 kilometers per second, would exhibit behavior that looks less like natural outgassing and more like controlled vectoring. Here's the question that will haunt you. Is 3I Atlas a pristine relic, a frozen archive of whatever chemistry existed in the disk around its parent star 4 billion years ago? Or is this alignment, this impossibly convenient observational window, this anti-minus tail aimed at Earth, these symmetric emissions, not a coincidence at all? Because if the alignment wasn't a coincidence, if the photographs, then someone or something knew we'd be watching. The universe has just handed us a choice: accept an extraordinary stack of geometric flukes, or consider the possibility that we're not observing 3I Atlas, it's observing us. If you're as gripped by this interstellar mystery as I am, hit that like button and subscribe. Drop a comment below and tell me, do you think 3I Atlas is a natural phenomenon? Or is this alignment deliberate? Because the data coming in this week might force us all to choose a side. In 7 days, the phase angle will widen. The opposition surge will fade. The anti-minus tail will blur back into the general coma of dust and gas. And 3I Atlas will accelerate outward, past the orbit of Jupiter, beyond the reach of our most powerful telescopes, carrying its secrets back into the interstellar void. This is the only chance we get. The only moment in human history when the geometry lines up, when the instruments are ready, when the light bouncing off this object can tell us whether we're looking at frozen chemistry or something that was designed to look back. The clock is ticking, the telescopes are tracking, and somewhere out there, to 0.87 astronomical units away, 3I Atlas is reflecting sunlight in patterns that will either confirm our cosmic loneliness or shatter it completely. Let's find out what's really out there. There's a moment in every detective story when the investigator stops relying on witnessed testimony and starts examining physical evidence, fingerprints, fiber analysis, blood spatter patterns, the stuff that doesn't lie, that can't be confused by memory or bias or wishful thinking. In astronomy, we're always working with circumstantial evidence. We can't touch these objects. We can run a spectrometer across their surfaces or drill core samples. All we have is light, is light, is light. Photons that traveled millions of kilometers to reach our detectors, carrying encoded information about what they bounced off before beginning that journey. Opposition surge is our forensic flashlight, and right now, it's illuminating something strange. Picture this: you're standing in a dark room with a powerful flashlight. In front of you is a surface covered in dust. If you shine the light at an angle, say 45 degrees, you'll see shadows. Every grain of dust casts a tiny shadow, and those shadows add up. The surface looks dim, textured, 3-dimensional. Now point the flashlight straight ahead, perpendicular to the surface. Suddenly, unfortunately, it's brighter. The shadows disappear because they're all hidden directly behind the grains casting them. You're seeing pure reflection. No shadow contamination. That's shadow hiding, and it's one of two mechanisms that cause opposition surge in astronomical objects. When 3I Atlas reached a phase angle of 0.16 degrees, we expected to see a brightness spike. Every comet, every asteroid, every dusty object in the solar system gets brighter at low phase angles. It's basic geometry. The question is, how much brighter? And what does the shape of that brightness curve tell us about the physical structure of the dust? Fluffy dust, pristine, unprocessed grains that have never been heated or compressed, produces a broad, gentle opposition surge. The brightness increases gradually as phase angle decreases, following a predictable curve. This is shadow hiding in action. The dust particles are irregular, porous, separated by empty space. They scatter light in all directions, and the shadows between them dominate until you're looking almost straight back at the light source. Compact dust tells a different story. If the grains are small, uniform, and tightly packed, if they've been processed by heat or compression, or some other mechanism that removes porosity, you get coherent backstater. This is a quantum mechanical effect, not just geometry. Light waves reflecting off densely packed grains interfere with each other constructively, amplifying the return signal in a narrow cone directly back toward the light source. Coherent backstater produces a sharp, intense opposition surge. The brightness spikes dramatically within a few degrees of zero phase angle, then drops off quickly as you move away from perfect alignment. It's the difference between shining a flashlight on fresh snow versus shining it on a mirror. Snow gives you diffuse reflection. A mirror gives you a concentrated return beam. Here's why this matters for 3I Atlas. The multi-band photometra data coming in from Monarchy shows a brightness increase of 0.3 for magnitudes between phase angles of 2.1 degrees and 0.69 degrees. That's significant. That's steep. The preliminary curve fit suggests we're seeing something closer to coherent backstater than shadow hiding, which means the dust around 3I Atlas might not be fluffy and pristine. It might be compact, processed, uniform at an microscopic scale. Let me walk you through what the astronomers are actually doing this week. Because the technical precision here is staggering. They're measuring the brightness of 3I Atlas in 5 different wavelength bands: ultraviolet, blue, visible, red, and near-infrared. Each measurement is repeated hundreds of times per night to average out atmospheric turbulence and instrumental noise. The photometric precision is 0.008 magnitudes. That's less than a 1% variation in brightness. They're tracking changes smaller than the difference between a 61-watt light bulb observed from across a football field. Why 5 wavelength bands? Because the opposition surge isn't uniform across all colors. If you're seeing shadow hiding, the effect is roughly the same at all wavelengths. Geometry doesn't care whether photons are blue or red. But coherent backstater is wavelength minus dependent. Shorter wavelengths, blue and UV, show a more pronounced surge than longer wavelength, red, because the interference effects depend on the ratio between grain size and photon wavelength. The data is still being calibrated, but the preliminary results show exactly that pattern. The opposition surge is stronger in the blue, the curve is steeper in the ultraviolet. The red and infrared bands show less enhancement. That's coherent backstater, that's compact grains. And compact grains mean processing, pristine cometary dust. The stuff that's been frozen since the birth of the solar system is fluffy. It forms in the cold outer regions of protoplanetary disks where ice condenses onto microscopic seed particles, building up like frost on a window. The resulting grains are fractal aggregates, all surface area and empty space, like microscopic tumbleweeds. To get compact grains, you need heat, you need compression, you need some mechanism that takes those fluffy aggregates and sinters them into dense particles with smooth surfaces. In natural comets, this can happen near the nucleus surface where solar heating drives sublimation. The heat partially melts the icy matrix, allowing grains to pack together before being ejected. You see processed dust mixed with pristine dust, a gradient from the surface outward. But 3I atlases to 0.87 AU from the Sun right now. That's nearly 3 times Earth's orbital distance. The solar flux is less than 12% of what we receive. At that distance, water ice doesn't sublimate vigorously enough to produce the massive dust ejection we're observing. Carbon monoxide. Yes, carbon dioxide maybe, but not at the rate required to explain the brightness of the comet and the structure of that NT-tail. So where the 3I atlas has an unusual composition, supervolatiles that outgas far from the Sun, or the dust we are seeing isn't being produced by thermal sublimation at all. There's a third option, and it's the one that makes your rational mind uncomfortable. What if the dust isn't fluffy because it was never meant to be fluffy? What if you're looking at engineered surfaces? I know, that's a leap. That's the kind of speculation that gets you laughed out of a peer review. But follow the logics. If you wanted to create a structure that could survive interstellar transit, that could withstand micrometeor impacts and cosmic ray bombardment for potentially millions of years, you wouldn't use fluffy aggregates. You'd use dense, compact materials. You'd engineer surfaces with specific optical properties. And if you were approaching a star system inhabited by a technological civilization, and you wanted to maximize your visibility during a brief observational window, you might design those surfaces to produce a pronounced opposition surge, a brightness spike that says, "Look at me, I'm different, I don't scatter light like your native comets." That's the forensic flashlight hypothesis. And it's either genius minus level engineering or pure seeing patterns and noise, because our brains are wired to find intentionality in chaos. The data will tell us which. By the end of this week, we'll have enough phase angle coverage to fit the brightness curve with high confidence. If it's a narrow spike, if the enhancement is concentrated within 1 degree of opposition and drops off sharply, then we're looking at compact grains, period. The physics doesn't lie. What we do with that conclusion is where the detective work begins. Let me show you a picture you can't see. Right now, if you had access to one of the major observatories tracking 3I atlas, you'd be looking at a diffuse coma, a cloud of gas and dust maybe 80,000 kilometers across with 2 tails streaming away from it. One tail is broad and curved, yellowish in color, made of dust grains pushed by solar radiation pressure. This is the Type II tail, standard equipment for any self-respecting comet. It follows the comet's orbital path, lagging behind because the dust particles have mass and inertia. The other tail is narrow and straight, bluish, made of ionized gas molecules accelerated by the solar wind. This is the Type I tail, always pointing directly away from the Sun regardless of the comet's motion. CO ions, the ions. Mostly carbon monoxide stripped of an electron, flossing in ultraviolet light. These are the expected tails, the normal tails, the tails that make sense. and then, jetting forward from the coma toward the sun, there's a third structure, the anti-tail. It looks like a thin spike, maybe 0 kilometers long, brighter than the surrounding coma but fainter than the main dust tail. It appears to defy physics, pointing in the wrong direction, as if the comet is somehow spraying material toward the very thing that should be pushing it away. But it's not defying physics, it's defying your perspective. Here's what's actually happening. 3I Atlas, like all comets, is shedding dust into the plane of its orbit. That dust forms a thin sheet, maybe only a few hundred kilometers thick but millions of kilometers wide, spreading out along the comet's trajectory. Most of the time, we see that sheet from an angle. We're above it or below it, and it blends into the general coma and tail structure. But when Earth crosses through the plane of the comet's orbit, or gets very close to it, we see the dust sheet edge minus on. Suddenly, all those millions of kilometers of dust collapse into a thin line in our field of view. The geometry creates the illusion of a spike pointing toward the sun. Anti-tails are rare but documented. Comet Rand-Roland in 1957th, Comet Hale-Bopp in 1997th, maybe a dozen others in the modern observational record. What makes 3I Atlas different is the timing. The anti-tail became visible on January 18th, for days before opposition. It reached maximum prominence on January 22nd, the exact day of minimum phase angle, and it's aligned with Earth to within 0.3 degrees. Let's unpack that coincidence. For the anti-tail to be visible, Earth needs to be near the plane of 3I Atlas's orbit. That orbital plane is tilted at 47.2 degrees relative to the ecliptic. The plane of Earth's orbit. We cross through that plane or come close to it at the point along our annual path around the sun. The opposition occurred at one of those crossing points. That's coincidence number one. The geometry that creates the anti-tail illusion happens to align with the geometry that creates the optimal viewing angle for opposition surge. But here's where it gets forensic. The anti-tail isn't just visible, it's aimed at us. When you measure the position angle of the spike relative to the background star field, it points to within 0.3 degrees of Earth's location, not toward the sun, which would make sense if it were just a matter of orbital plane intersection, toward Earth specifically. How do you aim an anti-tail at Earth? You don't. The anti-tail is a geometric projection, an illusion created by viewing angle. It doesn't have a direction in the way a jet has a direction. It's just our line of sight intersecting the dust sheet, unless the dust sheet itself is structured. Let me give you the natural explanation first, because it's important to be fair. If 3I Atlas has been shedding dust asymmetrically, maybe from active regions clustered on one hemisphere, then the dust sheet isn't uniform. It has clumps, gaps, density variations. When we look edge minus on through that sheet, we're seeing those variations projected along our line of sight. A denser region appears brighter. If that denser region happens to be located such that our sightline through it also points roughly toward Earth, you get the appearance of a spike aimed at us. The probability of this configuration isn't 0. It's just low. You need it this low. You need is an Abiraj, an interstellar object passing through the inner solar system Rhea. A trajectory that brings it into opposition with Earth in common. Opposition occurring when Earth is near the object's orbital plane-specific geometry. A symmetric dust emission creating a density enhancement plausible. That enhancement positioned such that the edge minus on view aligns with Earth lucky. Stack those probabilities together, and you get something like 1 minus in minus several minus 1,000. Not impossible. Not even implausible if you're willing to accept that we happen to be living in the timeline where the dice came up right. But there's another way to create a directed anti-tail. If the dust isn't being ejected passively by sublimation, but actively by some form of directed emission jets, vents, controlled outgassing, then you can shape the dust sheet. You can create density enhancements where you want them. You can, in principle, aim the structure that will become visible when viewed edge-on. This is the engineering hypothesis, and it requires assuming that 3I Atlas has the capability to control its dust emission with spatial precision. Which brings us to the jets. On January 20th, 2 days before opposition, the Subaru telescope on Mauna Kea captured a high-minus resolution image of 3I Atlas using adaptive optics to compensate for atmospheric distortion. The image was processed using a Laplacian filter to enhance fine structure in the coma. 3 features appeared: narrow, linear enhancements in brightness, extending from the central nucleus outward into the coma, evenly spaced around the nucleus, separated by approximately 120 degrees. The initial report was cautious. Possible jet structures detected. Further analysis required to rule out instrumental artifacts. The next night, the Very Large Telescope in Chile imaged the same object using a different camera, different optics, different processing pipeline. 3 features, same spacing, same morphology. Then the Atacama Large Millimeter Array weighed in with radio observations, mapping carbon monoxide emission. 3 lobes of enhanced CO concentration, spatially coincident with the optical features. 3 independent instruments, 3 different wavelengths. Same result. The jets appear to be real. Now comes the smell test. Comets have jets. This is not controversial. When sunlight heats the surface of a cometary nucleus, subsurface ices vaporize and burst through weak spots in the crust, dragging dust within. These jets are driven by thermal gradients and structural failures. Random geology meeting random solar heating. Natural jets are messy. They turn on and off as the nucleus rotates, exposing different regions to sunlight. They cluster on the side facing the sun because that's where the heat is. They vary in intensity based on the composition and porosity of the surface material. They don't arrange themselves in symmetric patterns because random geology isn't symmetric. The jets on 3I Atlas violate every one of those expectations. First, they're evenly spaced. 120 degrees apart means 3-fold rotational symmetry. That's the geometry you get from a triangular prism, a 3-bladed propeller, a structure designed with intentional angular relationships. Natural nuclei are potato-shaped, irregular, fractured by impacts and thermal stress over billions of years. They don't have 3-fold symmetry. Second, they're stable. The same features appear in images taken 24 hours apart, which means they're either always active or they're tied to the nucleus's rotation period in a way that keeps them visible from our viewing angle. If the rotation period is exactly 24 hours, which would be a coincidence, the jets could be on the sun-facing hemisphere, rotating into and out of view. But preliminary light curve analysis suggests a rotation period of 8.7 hours. That means we should see the jets turn on-off 3 times per day. They don't. They're constant. Third, they're symmetric in brightness. Natural jets vary in intensity based on the local geology, how much ice, how porous the crust, how deep the active region. The 3 jets on 3I Atlas are the same brightness to within observational error, same morphology, same length, same opening angle. That's the smell test. When you see a natural process producing a result that looks engineered, you have to ask, what are the chances? Let me give you the engineering criteria, the framework that researchers use to distinguish between weird nature and probably not nature. Criterion 1.1. Stability. Does the structure persist over time? Does it maintain its configuration despite changing conditions? Natural processes are stochastic. They fluctuate. Engineered systems have control loops, feedback mechanisms, stabilization. If the jets stay symmetric across multiple rotation periods, across changing solar flux, across different heliostenic distances, that's evidence of active stabilization. Criterion to vectoring. Are the emissions directed? Do they point in specific directions relative to the nucleus's orientation or trajectory? Natural outgassing follows pressure gradients and surface topography. Engineered emissions can detected and collimated. If the jets are aligned with the rotation axis, or perpendicular to it, or positioned to create a specific thrust profile, that's evidence of intentional orientation. Criterion 3. Timing. Is there a pattern to when the jets activate? Natural jets turn on when sunlight hits the surface. If the jets on 3I Atlas activate according to some other schedule synchronized with the opposition geometry, or pulsed at regular intervals unrelated to rotation, or coordinated across all three vents, that's evidence of non-thermal triggering. We don't have enough data yet to evaluate criteria 2 and 3 definitively, but criterion 1 is already raising eyebrows. The jets are too stable, too symmetric, too persistent. And then there's the velocity problem. Remember, 3I Atlas is moving at 57.7 kilometers per second relative to the Sun. At that speed, every action has consequences. If you're ejecting material from one side of the nucleus, you're creating thrust. Newton's third law doesn't care whether you're a comet or a spacecraft, equal and opposite reactions apply. Natural comets stumble because of asymmetric outgassing. Every jet is a tiny rocket engine firing at random, pushing the nucleus in unpredictable directions. Over time, the rotation rate changes, the spin axis wobbles, the trajectory shifts. But 3I Atlas is stable. The jets are symmetric. The rotation appears regular. If you're moving at 57.7 km/s and you want to maintain stable, symmetric emissions, you need active control. You need thrusters that can compensate for perturbations. You need a guidance system that can sense orientation and adjust firing patterns. You need engineering. And this is the natural explanation. You need an incredibly lucky configuration. A nucleus with 3 active regions that just happen to be evenly spaced. A rotation axis aligned such that all 3 regions see the same solar flux. A composition and porosity distribution that makes all 3 regions outgas at the same rate. A trajectory that minimizes torque from those emissions. It's possible, it's just precise. And precision in nature usually means you're selecting from a very large sample. One nucleus in a million might have this configuration. We've just happened to catch the one. But there's one more piece of evidence, and it's the one that bothers me most. The polarization data. When light scatters off dust grains, it becomes partially polarized. The degree of polarization depends on the grain size, shape, and refractive index. For cometary dust irregular, fluffy aggregates, you expect low polarization, maybe 5–10% at moderate phase angles. 3I Atlas is showing 23% polarization at a phase angle of 1.2 degrees. That's high. That's really high. High polarization means the dust grains are either very uniform in size or preferentially aligned in orientation. Uniform size happens when grains are processed, heated, compressed, sorted by aerodynamic drag during ejection. Preferential alignment happens when grains are elongated and rotating in a magnetic field, or when they're subjected to a directed force that orients them. Both scenarios point away from pristine, chaotic dust and toward processed, organized particles. And if the grains are organized, something organized them. Here's where the opposition surge suggests compact grains. The anti-stale is aimed at Earth during a geometrically optimal window. The jets are symmetric and stable. The polarization is anomalously high. And all of this is happening at 57.7 kilometers per second, a velocity that makes structured behavior harder to maintain. Each piece of evidence has a natural explanation, but the combination, the stack of coincidences, the precision required for all of them to occur simultaneously starts to strain credulity. This is the point in the detective story where you lay out all the evidence on a table and ask, what's the simplest explanation that accounts for everything? And the answer might not be the one you want to hear. Let's start at the bottom of the suspicion ladder. Level 1 is where most astronomical anomalies live, the zone of weird but explainable. This is where you find unusual chemistry, rare configurations, edge cases that textbooks mention in footnotes, but that absolutely can occur in nature. At level 1, 3I Atlas is just a comet with strange dust. Strange doesn't mean impossible. The universe has been running chemistry experiments for 13.8 billion years across trillions of star systems. Somewhere in that vast laboratory, conditions existed that produced dust grains with unusual properties. Maybe 3I Atlas formed in the outer disk of a carbon-rich star where graphite condensed into perfectly spherical particles. Maybe it accreted in a region with strong magnetic fields that aligned elongated grains during formation. Maybe it experienced a collision early in its history that melted and solidified its surface, creating a veneer of processed material. The spectroscopy's data gives us clues. When sunlight passes through the coma of 3I Atlas and reaches our telescopes, it's been filtered by the gas and dust. Certain wavelengths are absorbed, others are scattered. The resulting spectrum, a graph of brightness versus wavelength, is a fingerprint of the chemical composition. The preliminary spectrum shows strong emission lines from carbon monoxide, cyanogen, and diatonic carbon. It's typical for comets, especially those that formed in the outer regions of protoplanetary disks where carbon-bearing volatiles condense readily. But there's an anomaly in the continuum, the smooth background on which those emission lines sit. Cometary dust reflects sunlight in a way that's reddish. The reflection spectrum slopes upward toward longer wavelengths because the grains scatter blue light less efficiently than red light. This is the same reason Earth's sky is blue. Small particles preferentially scatter short wavelengths. The dust around 3I Atlas is neutral. The reflection spectrum is flat across visible wavelengths. That means the grains are either larger than typical cometary dust in the micron- to -millimeter range, rather than sub-micron or they're made of material with an unusually high refractive index. Large grains are easy to explain. If the nucleus is ejecting material gently, without violent outbursts, then gravity can winnow out the small grains as effectively. You end up with a size distribution weighted toward larger particles. But large grains shouldn't stay suspended in the coma. They should fall back to the nucleus or get swept into the dust tail quickly. The fact that we're seeing a dense coma implies continuous production of large grains, which requires continuous ejection at 2.87 AU from the sun. Continuous ejection means you need a lot of volatile material sublimating. Water ice doesn't cut it at this distance, it's too cold. You need carbon monoxide, which sublimates at much lower temperatures. Here's where it gets interesting. The amount of CO emission we're detecting doesn't match the dust production rate. Let me quantify that. Based on the brightness of the CN emission line, cyanogen is a good tracer for overall gas production. We estimate 3I Atlas is producing about 800 kilograms of gas per second. That's vigorous but not extraordinary. But the dust mass in the coma, estimated from the scattered sunlight, is around 40,000 kilograms. If the nucleus has been active for the past month, which is when we first detected the coma, and the dust is being produced continuously, then the dust minus to minus gas ratio is roughly 10 to -1. That's backwards. Normal comets have dust minus to minus gas ratios between 0.1 to -1 and to minus first, more gas than dust, because gas is what drives the ejection. For 3I Atlas to have a 10 to -1 ratio, either the gas is escaping without being detected, maybe in wavelengths we're not monitoring, or the dust is being ejected by a mechanism that doesn't require large amounts of gas. Or there's a third option. The dust was ejected in a single event, and we're just seeing the debris cloud now. This is the ice volcano hypothesis. Some comets, particularly those rich in carbon monoxide, can experience explosive outbursts when subsurface pressure builds up and fractures the crust. The stored gas erupts violently, dragging dust with it, and then the activity subsides. You're left with a cloud of dust that slowly disperses while the gas fades. If 3I Atlas had an outburst 2 or 3 weeks ago, that would explain the high dust minus to minus gas ratio. The gas has already dissipated. We're seeing the afterglow. It would also explain the symmetry jets. If the outburst occurred from three vents that fractured simultaneously, maybe along pre-minus existing stress lines in the crust due to gitsometric ejection, not because of engineering, but because the nucleus happened to fail in a symmetric way. Happened to fail. That phrase carries a lot of weight. But let's stay at level 1. Let's assume nature got lucky. The nucleus had 3-fold symmetry in its internal structure. Thermal stress built up evenly. The fractures occurred at 120-degree intervals. The ejected dust had unusual optical properties because of the specific chemistry in 3I Atlas's formation region. All of this is physically plausible. Unlikely, yes, but not impossible. The question is, how many unlikely things are you willing to stack before you climb to level 2? Level 2 is where coincidences start to demand explanation. At level 2, 3I Atlas isn't just weird, it's weird in ways that correlate with our ability to observe it. Let's revisit phase angle curve. This is the graph of brightness versus phase angle. And it's the key diagnostic for opposition surge. By measuring how much brighter the object gets as phase angle decreases, you can infer the physical properties of the scattering particles. The data from the past week now includes phase angles from 5 degrees down to 0.69 degrees with the dense coverage around opposition. The curve has been fitted with two models, a shadow-hiding model and a coherent-backstater model. The shadow-hiding model doesn't fit. The chi-squared value, a statistical measure of how well the model matches the data, is 8.7. Anything above 2.0 suggests a poor fit. The model predicts a gradual increase in brightness that doesn't match the sharp spike we observe. The coherent-backstater model fits beautifully. Chi-squared of 1.1. The parameters derived from the fit indicate grain sizes around to 5 microns with a refractive index of 1.6-1.8. That refractive index is high for cometary dust. It's consistent with silicates, but not fluffy silicate aggregates. Compact crystalline grains, processed material. Here's the kicker: coherent backstater only works if the grains are packed densely enough that their separation is comparable to the wavelength of light. For visible light around 500 nanometers, you need grains spaced less than a micron apart. In a natural cometary coma, dust grains are ejected at different velocities and quickly spread out. After a few days, the average separation is tens to hundreds of microns. Too far apart for coherent backstater. Unless the grains were ejected in a tightly collimated beam and haven't had time to disperse. Or unless there's a mechanism keeping them confined. Magnetic fields, electrostatic forces, something that prevents the natural expansion of the coma. Natural comets don't have mechanisms. They're passive. They outgas gravity and radiation pressure take over, and the coma expands freely. But let's hypothesize that 3I Atlas isn't passive. That it has a weak magnetic field, maybe from residual magnetization in its interior, and that field is shaping the dust distribution. Magnetic fields can align dust grains if the grains contain iron, and if the grains are aligned, they can scatter light preferentially, producing the high polarization we observe. This is still level 2, still natural. Just invoking a rare condition, a magnetized interstellar comet. But now add the rotation period. The light curve. The variation in brightness as the nucleus rotates shows a period of 8.73 hours with an amplitude of 0.1 to magnitudes. That's a modest variation, suggesting the nucleus is only slightly elongated, with an axis ratio of maybe 1.3 minus to minus 1. 8.73 hours is slow for a small body. Most cometary nuclei in the 1-5 kilometer size range, which is the estimated size for 3I Atlas, rotate much faster, with periods of 10 hours being common but typically on the shorter end. Slow rotation means high angular momentum relative to the nucleus mass. Something spun this object down, or it formed with unusually low rotation. Here's where the trajectory matters. 3I Atlas is on a hyperbolic orbit with an eccentricity of 1.034. That means it's unbound. It entered the solar system from interstellar space and will leave again. The orbital inclination is 47.2 degrees, and the argument of Perilhana places it on a trajectory that brought it into opposition with Earth precisely when Earth was near the orbital plane. What are the odds? Let's be rigorous. The sky has for steradianness of solid angle. Earth's orbit subtends a band roughly 0.1 steradianness wide, accounting for our orbital inclination range. For an interstellar object entering from a random direction to have an orbital plane that intersects Earth's position during opposition, you're selecting from about to 0.5% of possible trajectories. Now factor in the timing. Earth takes 365 days to orbit the Sun. The opposition window, the period when phase angle is below 2 degrees, lasts about 10 days. So you need the object to reach Perilhana, a closest approach to the Sun, within a 5-day window that aligns with Earth's position. That's another 2.7% probability. Multiply then 0.0 to 5 0.0 to 70. 68th, 1 in 1500. Not astronomical odds. Not impossible, but not trivial either. Now add the fact that this opposition occurred when the object is at 0.87 AU, far enough from the Sun that water ice doesn't sublime, but close enough that CO does. Too close, and the nucleus would have been destroyed by thermal stress during previous passes if this isn't its first visit to the inner solar system. Too far, and we wouldn't detect the coma at all. The distance is optimal for observation, the geometry is optimal for opposition surge. The timing is optimal for our current telescope capabilities and the ongoing surveys that discovered the object in the first place. Level 2 is where you start asking, is the universe conspiring to make this object visible? Or is the object conspiring to be visible? Level 3 is where we stop talking about individual anomalies and start talking about patterns, correlations, behaviors that repeat or follow rules. The symmetric jets are the smoking gun for pattern recognition. If the jets were, and outgassing vents, we'd expect them to vary. One vent might be stronger than another. They might turn on and off independently as the nucleus rotates. They might cluster on one hemisphere. But the jets are locked. They maintain their 120-degree spacing across every observation. They don't vary in brightness relative to each other by more than 5%, which is within photometric error, and they're always active. Let me show you what always active means in practice. The nucleus rotates every 8.73 hours. If the jet's a surface features specific vents on the crust, then each jet spends, if it's time facing the Sun and half its time facing away. When a jet is on the night side of the nucleus, it shouldn't be visible. Solar heating can reach it, so there's no thermal driver for outgassing. But the jets don't disappear. They fade slightly, maybe 15–20% dimmer when they rotate to the night side, but they remain visible. That means either the jets are being driven by internal heat, not solar heating. The nucleus has a warm interior that's sublimating volatiles from below the surface, and the jets are cracks that allow that gas to escape regardless of solar illumination. Or the jets aren't tied to the rotation. They're not surface features. They're structures in the coma itself, sustained by continuous emission from multiple vents that happen to align in such a way that the projected pattern looks the same from our viewing angle. Or see, the jets are aimed. They're directional emissions that track the Sun or track Earth, compensating for rotation to maintain a constant configuration. Option A is natural but requires a heat source. Radioactive decay from long-lived isotopes could provide some internal warmth, but not enough to drop to vigorous outgassing at this distance from the Sun. You'd need a recent event, a collision within the past million years that heated the interior, or compositional anomalies like a lumen -26, which decays rapidly and could have kept the interior warm if 3I Atlas is young. Option B is geometrically possible but statistically unlikely. You'd need the vents positioned just right. The rotation axis aligned just right, and our viewing angle just right. Triple coincidence. Option C is not natural. Aiming requires sensing and control. Let me define what aiming would look like operationally. If you're a jet on the surface of a rotating nucleus and you want to maintain a constant orientation relative to an external reference point like the Sun or Earth, you need to pulse. You fire when you're pointing in the right direction, and you shut off when you're not. The duty cycle, the fraction of time you're active, depends on how precisely you need to aim. For a jet to stay visible from Earth while the nucleus rotates, it would need to fire every time it rotates into view. That's a period matching the rotation period. 8.73 hours. The observations don't show pulsing. The jets are continuous. Unless the pulsing is happening faster than our temporal resolution. If the jets are firing in rapid bursts, say, every few minutes, and our exposure times are averaging over those bursts, we'd see a steady glow. Why would natural jets pulse rapidly? They wouldn't. Thermal cycling happens on hourly temescals as the surface rotates. Subsurface pressure builds slowly. There's no natural mechanism for rapid pulsation, but engineered systems can pulse. Thrusters, for instance. If you're using ejected material for attitude control, you'd fire short bursts to maintain orientation. This is speculation. I want to be clear about that. We don't have the temporal resolution to confirm or rule out rapid pulsing. But the fact that it's even plausible, that the data doesn't exclude it, puts us at level 3. Level 3 is where you're noticing patterns that natural processes don't typically produce. And then there's the timing of the anti-minus tail. The anti-minus tail became visible for days before opposition. It reached peak brightness at opposition. It's now fading as phase angle increases. That's a correlation. The anti-minus tail's visibility is tied to the phase angle. Geometrically, this makes sense. The anti-minus tail is an edge minus on view of the dust sheet, and edge minus on views are most prominent when our line of sight is perpendicular to the sheet. As phase angle changes, our viewing geometry shifts, and the anti-minus tail fades. But here's the question: why did the dust sheet form when it did? If the dust was ejected continuously over weeks or months, the sheet should be thickened, diffuse. We should see a broad, fuzzy anti-minus tail that persists across a wide range of phase angles. Instead, we see a narrow spike that appeared suddenly and is fading quickly. That suggests the dust was ejected in a pulse, a single event, or a series of closely spaced events that populated the orbital plane with fresh dust right before opposition. Coincidence, or timing. Natural comets don't know when opposition is coming. They outgas when the sun heats them, following a thermal curve that depends only on solar distance and rotation. There's no mechanism for a comet to know that Earth is about to line up with the sun, unless the outburst was triggered by something other than solar heating. Tidal stress. At 2.87 AU, the sun's tidal force on a kilometer-minus scale nucleus is negligible. You'd need to be inside the Roche limit. Less than 0.01 AU for tidal breakup. Impact. Possible. If 3I Atlas was hit by a small meteoroid in mid-January, that could fracture the surface and trigger an outburst, but the odds of an impact occurring within days of opposition are, well, we're back to stacking probabilities. Or the outburst was deliberate, timed, controlled. Level 3 is where you start using words like deliberate. Level 4 is not a place you go lightly. Level 4 is where you abandon natural explanations and start asking whether you're looking at technology. Let me define terms, because technology is a loaded word and precision matters. A techno- signature is observational evidence of engineering that cannot be explained by known natural processes. It's the inverse of a biosignature. Instead of looking for life, you're looking for intelligence. Specifically, intelligence that builds things. The key word is cannot, not as unlikely to be explained or as hard to explain. Cannot. You need to exhaust the natural hypotheses, rule them out with confidence, and be left with a residual that demands an engineered explanation. For 3I Atlas, What would that residual look like? Here are the criteria, the checklist that researchers use when evaluating potential techno- signatures. Criterion 1: repeatably. Does the behavior occurrence that are too regular to be random? Natural processes are stochastic. They have noise, variability, chaos. Engineered systems have control, regulation, precision. If the jets pulse at exact intervals. If the outbursts synchronize to the millisecond. If there's a periodicity that doesn't match any known natural cycle, that's a flag. Criterion to complexity. Is the structure more organized than entropy allows? Natural systems tend toward disorder unless energy is being input to maintain structure. If 3I Atlas is maintaining symmetric jets across multiple rotation periods, across varying solar flux, across a trajectory that imposes changing stresses, then energy is being expended to sustain that symmetry. Where is the energy coming from? Criterion 3 is functionality. Does the behavior accomplish something? This is the hardest criterion because it requires you to infer intent. But if the jets are connected such that they create thrust in a specific direction, if the dust is being ejected to maximize brightness during opposition, if there's a correlation between behavior and observational geometry, then you're seeing functionality purpose. Criterion for exclusion. Have you ruled out all natural explanations? Not just the likely ones, but all of them. This is the burden of proof. You can't claim a techno- signature until you've systematically eliminated mundane causes. Let's apply these criteria to 3I Atlas. Repeatably, the jets are stable across at least 5 rotation periods, the duration of continuous observation. They don't vary in intensity beyond 5%. They maintains pacing to within 2 degrees. That's not conclusive, but it's suspicious. Complexity 3-fold symmetry is rare in natural nuclei. Maintaining that symmetry while rotating and outgassing requires either extreme lock or active stabilization. We don't have proof of stabilization, but we also don't have a natural mechanism that produces this level of order. Functionality. Here's where it gets uncomfortable. If the outburst was timed to maximize visibility during opposition, that's functional. If the anti-stale is structured to create a brightness enhancement when viewed from Earth, that's functional. If the compact grains are designed to produce coherent backdata, that's functional. But all of these require assuming intent, which is a leap. Exclusion. We haven't exhausted natural explanations. The ice volcano hypothesis still viable. Magnetic alignment is possible. Coincidence is always an option. We're not at level 3 yet by strict criteria, but we're close, uncomfortably close. Let me give you the thought experiment that keeps astronomers awake at night. Suppose you're an interstellar probe. You've been traveling for millions of years, crossing the light minus years between stars at a fraction of the speed of light. You're inert, dormant, conserving energy because you don't know when you'll encounter something worth waking up for. Then you enter a star's system. You detect electromagnetic emissions, radio, optical, infrared signatures of technology. You're approaching a civilization. What do? If your mission is observation, you want to gather data. You want to see this civilization up close, understand their technology level, assess whether they're worth contacting. But you also want to remain ambiguous. You don't want to cause panic, cultural disruption, premature contact. So you disguise yourself, you mimic a natural object. You activate slowly, subtly, in ways that could be mistaken for cometary activity. And you time your brightest display for the moment when you're best positioned to observe them while they observe you. Opposition. When the geometry is optimal. When their telescopes are pointed your way. You make yourself visible, but not obviously artificial. You create patterns that will make their scientists argue, debate, second-guess. You give them plausible deniability. This is the zoo hypothesis. The idea that extraterrestrial intelligence observes us without revealing itself, maintaining ambiguity to avoid contaminating our development. It's unfalsifiable, which makes it bad science. But it's also the scenario that fits the data if you're willing to climb to level 4. Here's where I need to be honest with you. I don't know if 3i Atlas is natural or artificial. No one does. The data is incomplete, the statistics are marginal, and the conclusions are still being debated in conference rooms and email threads across the astronomical community. What I know is this 3i Atlas is behaving in ways that cluster at the boundary between weird nature and possible engineering. Every individual anomaly has a natural explanation, but the combination, the stack, the correlation, the timing pushes the probability envelope. And in 7 days the window closes. The phase angle widens, the opposition surge fades. And 3i Atlas accelerates back into the dark. If we're going to answer this question, we have to answer it now, which means we need to talk about the tools we're using, the instruments, the algorithms, the processing pipelines that turn rough outcomes into scientific conclusions. Because there's one more possibility we haven't addressed. What if none of this is real? What if we're seeing ghosts in the machine? There's a photograph you need to see, except it doesn't exist. In 1967, astronomers at the Resemble Observatory detected a repeating radio signal from space. The pulses arrived every 1.337 seconds with mechanical precision. For 3 weeks, the team debated whether they'd found evidence of an extraterrestrial civilization. They nicknamed the source Algae-1 little green men. It wasn't aliens. It was a pulsar rotating neutron star whose magnetic field beams radio waves into space like a cosmic lighthouse. Well, minus understood physics producing a pattern that looked designed. The lesson wasn't that the astronomers were foolish. The lesson was that nature can mimic technology, and our instruments can lie to us in subtle ways. Right now across the world, teams are processing images of 3i Atlas. They're running those images through deconvolution algorithms, sharpening filters, contrast enhancement, noise reduction. Each processing step is designed to extract faint structure from noisy data, and each step introduces the possibility of creating structure that isn't there. Let me show you how easy it is to see ghosts. When a telescope captures an image, it's not recording a perfect representation of the sky. It's recording the sky as distorted by the telescope's optics. Every point source of light, every star gets blurred into a small disk by diffraction. This blur is called the point spread function, or PSF. The PSF is not symmetric. It has rings. Spikes, asymmetries caused by the shape of the telescope's mirror, the support struts holding the secondary mirror, even dust on the optics. When you're looking at a complex subject like a comet with a diffuse coma, the PSF of the bright nucleus gets convolved with the real structure of the coma, creating patterns that don't exist in reality. Deconvolution is the mathematical process of trying to remove the PSF, to recover the true image from the blurred observation. You're essentially solving an inverse problem given the observed image and a model of the PSF. What was the original light distribution? It works beautifully when the PSF model is accurate and the signal minus to minus noise ratio is high. It fails catastrophically when either of those conditions is violated. Here's what goes wrong. Deconvolution amplifies high minus frequency structure. Sharp edges, small details, anything that varies rapidly across the image gets enhanced. But noise also has high minus frequency components. So when you deconvolve a noisy image, you enhance the noise along with the signal. The result is ringing, spurious oscillations around bright features. Artificial halos, phantom structures that look like jets, but are actually mathematical artifacts of the processing. Let me give you a concrete example. In 2019, the Event Horizon Telescope released the first image of a black hole. It's an iconic image, glowing ring surrounding a dark shadow, but that image is not a photograph in the traditional sense. It's a reconstruction built from radio interferometry data, using sophisticated algorithms that fill in missing information. The team released 4 different reconstructions, each using a different algorithm. The ring appears in all of them, which is strong evidence that it's real, but the fine details, the brightness asymmetries, the exact shape of the photon ringing, vary between reconstructions. Those variations are algorithm artifacts. They're showing you what the algorithm thinks the image should look like based on its built minus and assumptions, not necessarily what's actually there. Now apply that lesson to 3i Atlas. The symmetric jets appear in images that have been decoupled, the raw images before processing. Show a fuzzy blob with hints of asymmetry but no clear jet structure. The jets emerge after you apply a Laplacian filter, which enhances edges, or a Lucy-Richardson deconvolution, which sharpens point sources. Are the jets real, or are they artifacts of the processing? Here is how you find out. You process the same data with multiple independent algorithms and see if the jets appear in all of them. If they do, that's evidence they're real. If they only appear with certain processing techniques, that's a red flag. The teams analyzing 3i Atlas have done exactly this. They've run the images through 5 different deconvolution algorithms: Lucy-Richardson, maximum entropy, Wiener filtering, blind deconvolution, and a neuromachine-learning-based approach. 4 out of 5 show the jets. The maximum entropy method shows only 2 jets, not 3, and places them at different position angles. That's not a smoking gun for artifacts, but it's a yellow flag. It suggests the third jet might be marginal, possibly enhanced by noise in the specific algorithms that reveal it. But then there's the ALMA data. ALM at the large millimeter array doesn't take pictures in the traditional sense. It measures radio emission from molecules like carbon monoxide. There's no PSF in the optical sense, no deconvolution required. The spatial resolution comes from interferometry, combining signals from multiple antennas. And ALMA sees 3 lobes of CO emission. Same position angles as the optical jets, same morphology. That's independent confirmation. Different wavelength, different instrument, different processing. If the jets were purely optical artifacts, ALNA wouldn't see them, unless ALNA is also lying to us. Radio interferometry has its own artifacts. When you combine signals from antennas spaced kilometers apart, you're sampling the Fourier transform of the sky brightness distribution, but you're not sampling it completely. You have gaps, missing baselines, regions of Fourier space that aren't measured. When you reconstruct an image from incomplete Fourier data, you get side lobes. These are faint copies of bright sources, displaced from their true positions, appearing in a pattern determined by the antenna configuration. For ALNA, observing 3i Atlas, the antenna configuration produces a specific side lobe pattern. And if you're not careful, those side lobes can look like symmetric structures around a bright central source. The ALNA team knows this. They've simulated the side lobe pattern for their specific observation and subtracted it from the data. The 3 lobes persist after side lobe removal, but simulations rely on models. If your model of the side lobe pattern is incomplete, if there are second minus order effects you didn't account for, the subtraction might be imperfect. You could be leaving behind residuals that coincidentally align with the optical jets. This is the paranoia that good science requires. You question everything. You assume your instruments are lying until proven otherwise. So let's push further. If the jets are artifacts, optical and radio artifacts that happen to align, then they should disappear when you look in other ways. Spectroscopy, for instance. When you disperse the light from 3i Atlas through a spectrograph, splitting it into a spectron, you are no longer relying on imaging. You're measuring the intensity of specific emission lines as a function of position. If the jets are real, the gas in those jets should show up as spatially extended emission in COCN, SCN, or C to spectral lines. Preliminary spectroscopy from the Keck Observatory shows ambiguous results. There's extended emission, but it's not clearly structured into 3 distinct lobes. It looks more like a broad, irregular coma with some asymmetry. The asymmetry could be consistent with jets, but it could also be consistent with uneven outgassing from a rotating nucleus. Not conclusive, not exonerating. And then there's the polarization problem. Remember the high polarization we discussed earlier? 20-3% at low phase angle. That's a hard number to fake. Polarization is an intrinsic property of scattered light. It doesn't depend on image processing or deconvolution, but it does depend on subtraction. When you measure polarization, you're comparing the brightness of an object into orthogonal polarization states. You subtract one from the other and divide by the sum. Any error in the subtraction, any slight misalignment of your polarizing filters, any differential atmospheric refraction between the two measurements gets amplified in that division. If your polarization measurement is contaminated by systematic errors, you can get spuriously high values. The observers calibrated their polarization using nearby field stars. The stars show low polarization, less than 1%, which is expected for starlight passing through our galaxy. That suggests the systematic errors are small. But 3i Atlas is extended. It's not a point source. The polarization could vary across the coma, and when you average over the whole object, you might be mixing regions with different polarization states. That mixing can inflate the apparent polarization. To rule this out, you need specially resolved polarimetry, measuring polarization within the coma. Those observations are scheduled for the next 2 nights, weather permitting. If the high polarization is confined to the jets, that's strong evidence that jets are real. If it's uniform across the coma, that suggests we're seeing a global property of the dust, not a jet-specific phenomenon. We're waiting on data, always waiting. Here's the brutal truth about astronomy: you're always working with incomplete information. You're trying to reconstruct a 3-dimensional time-varying, physically complex system from 2-dimensional projections captured in brief snapshots with instruments that barely have the sensitivity to detect the object in the first place. Every conclusion is provisional. Every result has error bars, and every anomaly could be an artifact. But artifacts follow patterns. They correlate with instrumental properties, processing choices, observing conditions. Real structures persist across different methods, different telescopes, different wavelengths. The jets on 3i Atlas have shown up in optical imaging, radio mapping, and tentatively spectroscopy. They've been observed from 3 continents using for different telescope systems. They've survived multiple processing pipelines. That doesn't prove they're real, but it raises the probability. The question is how much. Let me introduce you to the newest member of the team analyzing 3i Atlas. It doesn't have a name, just a model designation: GPT-Vision-Astra-4. 7th. It's a machine learning algorithm trained on 600,000 images of comets, asteroids, and other solar system objects. Its job is pattern recognition, feature extraction, anomaly detection, and it's terrifyingly good at finding things. Feed it an image of 3i Atlas, and within seconds it identifies the jets, measures their position angles, estimates their brightness, and classifies them as unusual. It flags the NT-tail, notes the high surface brightness of the coma, and even highlights subtle asymmetries in the dust distribution that human observers missed. It's the perfect tool for forensic astronomy, tireless, objective, sensitive to patterns that span spatial scales from pixels to arc-minutes. And it's also capable of hallucinating. AI hallucination is a term borrowed from neuroscience. It refers to the phenomenon where a pattern-recognition system, whether biological or artificial, perceives structure in noise. Your brain does this constantly. You see faces in clouds, hear words in static, find constellations in random star fields. Neural networks do it too, especially when they're optimized for high sensitivity. If you train a network to detect faint features, it becomes hypervigilant. It flags everything that even vaguely resembles the patterns it was trained on, and because it's operating on statistical inference rather than physical understanding, it can't distinguish between real features and artifacts. GPT-Vision-Astra-4.7 was trained on images of cometary jets. It learned to recognize linear enhancements and brightness radiating from a central nucleus. It learned that jets are often symmetric, often associated with active comets, oft invisible in multiple wavelengths. So when you show it 3-eye atlas, it expects to see jets, and expectation biases perception. Here's an experiment. Take the raw, unprocessed image of 3-eye atlas, the fuzzy blob before deconvolution. Feed it to the AI, ask it to identify jets. It finds 4 jets. 4, not 3. 2 of them match the position angles of the optically detected jets. The third matches the tentative jet seen in some processing pipelines. And the fourth is new, a faint feature extending to the northwest that hasn't been reported by human observers. Is the fourth jet real, or is the AI inventing it? You can't answer that question by asking the AI. The AI is a black box. It processes input, produces output, and the intermediate steps, the billions of weighted connections in its neural network, are inscrutable. You can't interrogate it. You can't ask, why did you think this was a jet? All you can do is test its predictions. The AI says there's a jet to the northwest. So you go back to the raw data, extract that region, apply manual processing techniques, and you find maybe something, a marginal enhancement, barely above noise. Could be a jet. Could be a brightness fluctuation in the coma. Could be a cosmic ray hit that wasn't perfectly removed. This is the AI problem. It finds patterns you wouldn't have noticed on your own, but you can't trust those patterns without independent verification, and independent verification is expensive, time-consuming, and not always conclusive. Now scale this up. Across the world, researchers are using AI to analyze astronomical data, to classify galaxies, detect exoplanets, identify supernovae, map dark matter. The algorithms are powerful, efficient, and increasingly autonomous. They're making discoveries faster than humans can vet them, and some fraction of those discoveries are hallucinations. A 2023 study estimated that approximately 8–12% of AI-detected anomalies in astronomical survey data are false positives, patterns the algorithm flagged as significant, but that don't correspond to real astrophysical phenomena. Some are instrumental artifacts, some are statistical flukes, and some are just noise that happen to resemble signal. For 3-eye atlas, we're using AI as a tool, not an oracle. The AI findings guide where we look, but the final judgment comes from human analysis of raw data, cross-checked against multiple independent methods. But here's what worries me: confirmation bias. Once the AI tells you there are 3 symmetric jets, you start seeing 3 symmetric jets. You process the data in ways that enhance those features. You interpret ambiguous signals as supporting evidence. You become invested in the narrative the AI handed you. And if the AI was wrong, and if it hallucinated the pattern based on noise, you're now locked into a false trail, expending resources chasing a ghost. This has happened before. In 2021, an AI system analyzing Kepler exoplanet 8 flagged a star with periodic dimming events that matched the signature of a transiting meganinous structure, a so- called Dyson swarm. The finding triggered months of follow-up observations, spectroscopy, interferometry, theoretical modeling. It was an artifact. The dimming was real, but it was caused by dust from a recent stellar collision, not artificial structures. The AI had been trained on exoplanet transits and had learned to recognize periodic patterns. When it saw periodic dimming, it classified it as a transit, even though the light curve had subtle differences that a human expert would have caught. The researchers published a retraction. The AI was retrained, less unlearned, but the cost was high, not in money, but in credibility. For years afterward, any AI-assisted discovery in exoplanet science was met with skepticism. Is this real? Or is this another hallucination? For 3-eye atlas, we can't afford that mistake. If we claim there's evidence of techno-signatures based on AI-detected patterns, and it turns out those patterns are artifacts, we don't just lose credibility. We poison the well, Future genuine anomalies will be dismissed as probably another 3i Atlas situation. So we're being paranoid. We're running the analysis both with and without AI assistance. We're blinding the human analysts to the AI results until they've completed their own independent assessment. We're requiring agreement between humans and machines before accepting any conclusion. It's slow, it's inefficient, but it's necessary, because the stakes are too high to get this wrong. Let me tell you what happens when you think you've found something extraordinary. First, you doubt yourself. You check your calibration. Run the processing. Verify that your software didn't crash halfway through and corrupt the output. You look for the stupid mistakes, the decimal point in the wrong place. The coordinate system flipped. The filter will stuck on the wrong setting. You find nothing wrong. The data is clean. Second, you tell a colleague, someone you trust. You send them the images with no commentary. Just what do you see? If they see the same thing you do, unprompted, that's the first confirmation. If they shrug and say looks normal to me, you go back to step one. Third, you check the archive. Has anyone seen this before and has missed it? Is there a paper from 1987 explaining this exact phenomenon as a known artifact? You search ADS the astrophysics state assistant, Wifistant, for every paper mentioning similar observations. You read dissertations. You email retired astronomers who worked on legacy surveys. Fourth, you build a model. Not a hand-waving explanation, but a quantitative physical model that reproduces the observation. If you can't build a model, you don't have a discovery, you have a puzzle. Fifth, you predict something. The model should make testable predictions. If this explanation is correct, then we should see X when we observe at Y wavelength or Z phase angle. You design a follow-up observation. You propose it to a telescope allocation committee. You wait months for approval and scheduling. Sixth, you observe again, with a different telescope if possible, different instrument, different hemisphere, different team processing the data. If the prediction is confirmed, you publish. If it's not, you go back to step 4. This is the truth protocol. It's slow, conservative, frustrating. It's designed to filter out errors, biases, and wishful thinking. It's why science works. For 3i Atlas, we're in step 5 right now. We have predictions. Prediction 1: if the opposition surge is caused by coherent backstator from compact grains, then the polarization should peak at 0 phase angle and show a specific wavelength dependence. Blue light should be more polarized than red light. Test polarimetry observations scheduled for January 25 and 5 wavelength bands. Prediction 2: if the jets are real and tied to the nucleus rotation, then their brightness should modulate with the 8.73 minus our rotation period. Each jet should reach maximum brightness when it's oriented toward Earth. Test: continuous photometry over 48 hours with 10-minute cadence, currently underway. Prediction 3: if the anti-tail is a dust sheet seen edge-on, then it should show no radial velocity variation. All the dust is moving with the same velocity as the nucleus. If it's a jet aimed at Earth, we should see velocity gradients from Doppler shifting. Test high-resolution spectroscopy of the CN emission line within the anti-tail scheduled for January 23. Prediction 4: if the compact grains are silicates, we should see a characteristic 10-micron emission feature in mid-infrared spectroscopy. If they're carbonaceous, the feature will be absent or shifted. Test JWST observations requested under director's discretionary time. Approval pending. Each test is independent. Each test can falsify the hypothesis, and if any test fails, we revise the model and start over. This is also where the techno-signature hypothesis runs into trouble. You can't test for technology directly. Technology is not a physical property you can measure like temperature or density. It's an inference based on exclusion. This behavior cannot be natural. Therefore it must be artificial. But cannot is a strong word. To claim something cannot be natural, you need to have exhausted all natural explanations. And how do you know when you've exhausted them? There's always one more mechanism you didn't think of, one more edge case, one more unusual configuration. Carl Sagan's dictum applies: extraordinary claims require extraordinary evidence. What would constitute extraordinary evidence for 3I Atlas being artificial? Here's a partial list, ranked from suggestive to conclusive. Level 1 - suggestive: multiple anomalies that correlate in ways inconsistent with any single natural mechanism. For example, if the jets require magnetic alignment A, and E the grains require thermal processing, A and E the tining requires coincidence, the combined probability becomes very low. Not proof, but enough to warrant serious attention. Level 2 - compelling repeated, non-random behavior over time. If 3I Atlas fires its jets in a sequence, first one, then two, then 3, cycling through, then through, rather than all at once, that's hard to explain naturally. Natural vents don't take turns. Level 3 - highly anomalous. Course corrections. If the trajectory changes in ways that can't be explained by outgassing thrust, if the object accelerates perpendicular to the sun direction, or if it makes a delta -v change larger than the available volatile inventory allows, you're looking at propulsion. Level from - conclusive information content. If the jets pulse in a pattern that encodes information, binary, prime numbers, mathematical constants that's unambiguous. Nature doesn't do mathematics. We're at level 1, maybe approaching level 2 depending on how the photometry analysis plays out. We're nowhere near level 4. And honestly, I'm not sure we want to be. Let me tell you what happens if we find conclusive evidence. The paper gets submitted. It passes peer review barely, with extensive revisions and caveats. It gets published in a top journal. The press picks it up. Headlines scream ALINPROBED, BTECTED, INSOLARSYSTEM. The public goes wild. Social media explodes. Conspiracy theories metastasize. Governments demand access to the data. The United Nations convenes a special session. Religious leaders issue statements. Stock markets fluctuate. And then the doubt sets in. Other teams analyze the data. Some confirm the results. Others find flaws, subtle calibration errors, unaccounted systematics, alternative explanations. Debates rage in the literature. Reputations are built and destroyed. Meanwhile, 3I Atlas continues its trajectory, indifferent to our arguments. It passes Jupiter's orbit, crosses the heliopause, fades into the infrared, then into radio silence, gone. We're left with data, interpretations, and no way to follow up. No way to send a probe to intercept it. No way to get a closer look. Just images and spectra and a million pages of analysis arguing over what we saw. And the question never gets answered, not definitively, because that's how science works when the object of study doesn't stick around to be measured. The truth protocol is designed for repeatable phenomena, for objects you can observe again and again until you understand them, for experiments you can replicate. 3I Atlas is not repeatable. It's a 1-time event, a unique configuration of geometry and timing that will never occur again in human history. So we do the best we can. We collect every photon. We build every model. We test every prediction. We argue, debate, scrutinize, and doubt. And at the end of the week, when the phase angle widens and the data stops flowing, we'll have our answer, or we'll have more questions. Either way, we'll know more than we did before. And that's the point. Let me show you how this could all be perfectly ordinary. Start with a comet nucleus, nothing exotic. Just a 4-billion-year-old ice ball, maybe 2 kilometers across, that formed in the outer disk of a star system 200 light-years from here. The disk was rich in carbon monoxide and carbon dioxide, volatiles that condense at low temperatures. Our comet accreted in the cold dark, accumulating layers of ice and dust, freezing solid, inert, for billions of years. It orbited its parent star in the Kuiper belt equivalent of that distant system. Stable, frozen, unchanging. Then something disturbed it. Maybe a passing star gravitationally perturbed the outer disk. Maybe a giant planet migrated inward and scattered objects into chaotic orbits. Maybe there was a collision to icy bodies slamming together at low velocity, transferring just enough momentum to push one fragment onto a hyperbolic trajectory. Our comet was ejected, cast out of its own system with a velocity of 20 kilometers per hour. It drifted into interstellar space, cooling to 10 Kelvin, silent and dark. For 2 million years it traveled, across 200 light-years, through molecular clouds and stellar winds in the thin, cold vacuum between the stars. No sunlight touched it. No heat disturbed its frozen interior. And then, by chance pure geometric accident, it entered our solar system. The sun's gravity bent its trajectory into a hyperbola, eccentricity 1.034, inclination 47 degrees, Perilhana at 1.8 AU, close enough for solar flux to start warming the surface. When 3I Atlas crossed 3 AU inbound, carbon monoxide ice began to sublimate. Not explosively, gently. As solar heat conducted into the subsurface and liberated gas from the pores between dust grains. The gas percolated upward, found pathways through the crust, vented into space. 3 pathways. 3 fractures in the crust, relics of ancient thermal stress or tidal encounters in the birth system. They happened to be spaced 120 degrees apart because the nucleus happened to have a roughly triangular cross-minus sectioned with sectioned. Not engineered, just the random geometry of how smaller particles aggregated during formation. The vents opened simultaneously, because they were at the same depth, subject to the same subsurface temperature. Thermal waves from solar heating propagate inward at a predictable rate. When the wave reached the depth where CO pressure exceeded the tensile strength of the overlying crust, all 3 vents failed at once. The dust ejected from these vents was unusual, because the nucleus composition was unusual. It formed from material that had been thermally processed in the inner disk of its birth system before being scattered outward. The grains were partially sintered, compacted by heat into dense particles with high refractive indices. Not engineered. Just cooked. These grains scattered light via coherent backstator because they happened to be ejected with low velocities just a few meters per second, and the electrostatic forces between them slowed their expansion. The coma remained dense enough for just long enough that grain separation stayed within a wavelength of visible light. Lucky, but not impossible. The high polarization, grain alignment by the weak magnetic field frozen into the nucleus during formation. Cometary nuclei can retain magnetization from their birth environment. If the field is strong enough and the grains contain ferromagnetic inclusions, they align. Natural, known physics. The anti-minus tail appeared during opposition because that's when Earth crossed the orbital plane. The dust sheet was already there. Weeks of continuous outgassing had populated the plane with particles. We just didn't see it edge minus on until the geometry lined up. The timing, coincidence. An interstellar object entering the solar system has some probability of reaching opposition during its passage. For 3I Atlas, the dice came up right. 1 minus in minus 15 minus 100 odds. Rare, but there are 1,500 interstellar objects passing through the galaxy at any given time. We noticed the one that happened to align. The rotation stability. The nucleus is dense and irregularly shaped, with a principal axis rotation state that's stable against perturbations. The outgassing is symmetric enough that the net torque averages to near zero over each rotation period. The object doesn't tumble because the geometry and mass distribution happen to favor stability. Stack it all up in usual composition from the birth environment. Favorable fracture geometry in the crust. Low ejection velocities creating dense grain populations. Weak magnetic field aligning particles. Trajectory bringing it into opposition. Rotation state maintaining stability. Each element is rare, but multiply enough rare probabilities across for billion years and billions of star systems, and you get outcomes that look designed but are merely selected. We're observing 3i Atlas not because it's typical, but because it's unusual enough to be noticed. This is the natural path, the conservative explanation, the one that doesn't require new physics or new assumptions about what exists in the universe. It fits the data, all of it. You don't need to invoke technology. You don't need to abandon Occam's razor. You just need to accept that sometimes nature rolls snake eyes. Now let me show you the other side. Suppose you're wrong about the probabilities. Suppose the odds of natural processes producing this exact configuration are 1 minus in minus 15 minus 100. Suppose when you account for all the correlations, the timing, the geometry, the dust properties, the rotational stability, the polarization, the jets, the actual probability is 1 minus in minus and minus a minus million, or 1 minus in minus a minus a minus billion. At what point does a likely become implausible? There's no sharp threshold, no magic number where coincidence transforms into evidence of design. But there's a principle in statistics called the Bayesian posterior. When you observe unlikely data, you should update your beliefs about which hypothesis generated the data. If the natural hypothesis predicts a 1 minus in minus a minus in minus a minus a billion outcome, and you observe that outcome, either you got extraordinarily lucky, or the natural hypothesis wrong. Let me walk you through what the alternative looks like. 3i Atlas is not a comet, it's a probe. Not a probe built last century or last millennium. A probe built onto mescals we don't think in millions of years ago, by a civilization that understood interstellar travel requires patience. The object left its origin system when Earth was inhabited by Australopithecus. It crossed the light minus years at a fraction of the speed of light, dormant, shielded, carrying no fuel because it doesn't need fuel. It's a sailcraft or a buzzard ramjet, or something we haven't thought of yet. Propulsion isn't the mystery is why. When it entered the solar system, it detected electromagnetic emissions. Radio leakage from our civilization, spreading outward at light speed. Its ichnological signature, evidence of intelligence. The probe adjusted its trajectory, subtly, a gravitational assist from an outer planet, time to bring it into the inner system on a path that would maximize observational opportunities. It approached the sun, heating up, outgassing volatiles it had carried as camouflage. The exterior is designed to mimic a natural comet. The dust it ejects is real dust, processed, uniform, engineered to produce specific optical properties when observed at opposition. The jets are not vents, they're attitude control thrusters. The symmetric spacing isn't coincidence, it's optimal configuration for 3- axis stabilization. The outgassing provides thrust, and the timing is controlled to maintain rotation rate and orientation. The anti-stale is deliberate. The probe shaped its dust emissions to create a structure that would be visible precisely when Earth passed through the orbital plane. A signal. Not language, not mathematics, just a pattern obvious enough to make us notice. Ambiguous enough to maintain deniability. Why deniability? Because revealing itself openly, broadcasting WEIRHE, REHE, would be destabilizing. First contact on our terms, not theirs. The probe is giving us the choice. Interpret this as natural or interpret it as artificial. Either way, we've been seen. This is the speculative path, the one that requires you to believe in things we have no direct evidence for. Interstellar probes, ancient civilizations, intentional ambiguity. But here's the thing, we already know interstellar probes are possible. We've built them. Voyager 1 and 2 are interstellar probes, primitive, slow, barely functional after for decades. But they exist. They're out there, carrying messages meant for whoever might find them millions of years from now. If we can do it with 1972 technology, what could a civilization do with 1,000 years of additional development? A million years. The speculative path doesn't require magic. It requires only that we're not alone, and that someone else thought to do what we've already done. Here's how you decide which path to believe. Start with the opposition surge. If the brightness curve shows an arrow spike, enhancement concentrated within 1 degree of zero phase angle, dropping off sharply at higher angles than you're looking at coherent backstater. That's established physics. The interpretation is unambiguous: compact grains tightly spaced. If you observe an arrow spike, then the grains are compact. Compact grains mean processing, heat or compression or some mechanism that renews porosity and creates smooth surfaces in a natural comet. Processing happens near the nucleus where solar heating is strongest. But 3I Atlas is at 2.87 AU. Solar flux is weak. Water ice doesn't sublimate vigorously at this distance. If the grains are compact at 2.87 AU, then the processing didn't happen recently. So either the grains were processed in the object's birth system pre-minus formed in a hotter environment and preserved during interstellar transit, or they're being processed by an internal heat source. Internal heat means radioactive decay, or chemical reactions, or stored energy from formation. For a 2-kilometer nucleus, radioactive decay from long-lived isotopes can provide a few watts of power, not enough to doctor vigorous outgassing. If internal heat is insufficient, then the grains were pre-minus formed. Pre-minus formed compact grains, surviving interstellar transit means the object is structurally robust. Fragile, fluffy material would be eroded by micrometeorite impacts and cosmic rays, puttering over millions of years. If the grains survived transit, then the object is robust. Robust objects are either solid rock, no volatiles, no outgassing, or they're protected, shielded by an outer crust, or composed of materials that resist erosion. If the object is robust and outgassing, then it has protective structure. Protective structure can be naturally thick crust of refractory material formed during the object's birth, or it can be designed. This is where the logic branches. The data forces you to choose. Now add the jets. If the jets are symmetric, evenly spaced, equal brightness, persistent across rotation, then they're either tied to symmetric geology or they're controlled. If the jets are symmetric, then the structure is symmetric. Natural nuclei aren't symmetric. They're fragments of collisions, aggregates of smaller bodies, carved by sublimation over billions of years. Symmetric geology is rare. If symmetric geology is rare, then observing it is unlikely. But unlikely isn't impossible. With billions of comets across billions of star systems, some will have symmetric fractures. We're observing one of them. Unless the symmetry is maintained actively. Unless the jets are being fired in a pattern designed to look symmetric from our viewing angle. If the symmetry is maintained, then energy is being expended. Maintained symmetry over days or weeks requires feedback. The system has to sense its orientation and adjust outgassing rates to compensate for perturbations. Natural systems don't have feedback. They're passive. They respond to external forcing, solar heating, rotation, but they don't regulate. If the system has feedback, then it has sensors and actuators. Sensors and actuators are technology. This is the logic grid. Each step follows from the previous one. Each step is either supported by data or constrained by physics. And at the end, you arrive at a conclusion that you can't escape without rejecting one of the premises. Either the data is wrong, artifacts, misinterpretations, systematic errors, or the physics is wrong, we're missing a natural mechanism that can produce these effects. Or the conclusion is right, 3I Atlas is not entirely natural. The phase angle is widening. Right now is wide now. As I'm recording this, it's at 1.8 degrees and increasing. By tomorrow, it'll be 2.5 degrees. The opposition surge is fading. The window is closing. But the data is coming in. The polarimetry observations completed successfully. 5 wavelength bands, high signal minus to minus noise. The results are being calibrated now, but preliminary numbers show the polarization does peak at zero phase angle, and it is stronger in blue than in red. That's consistent with coherent backstater. The grains are compact. The photometry analysis is still running. 40-8 hours of continuous monitoring tracking brightness variations with 10-minute cadence. If the jets modulate with the rotation period, we'll see it in the light curve, results expected within 24 hours. The high-resolution spectroscopy of the anti-stale showed no radial velocity gradient. The CN emission is Doppler-shifted by the same amount across the entire structure, within observational error. That's consistent with a dust sheet seen edge-on, not a jet aimed at us. 1 point for the natural explanation. But the JWST proposal was approved. Director's discretionary time, highest priority. Observations scheduled for January 26-27, just before 3I Atlas exits the optimal viewing window. Mid-infrared spectroscopy will reveal the composition of the dust grains unambiguously. Silicates, carbonaceous material, water ice, organics, everything has a spectral fingerprint at 10 microns. If the grains are silicates, that's consistent with natural cometary material. If there's something else, metal oxides, processed carbon, exotic ices, that raises new questions. We'll know in 3 days. And then there's the trajectory. Astrometry, precise measurement of 3I Atlas's position over time, allows us to calculate its orbit with increasing accuracy. The orbit determines whether the object is affected by non-gravitational forces. Outgassing creates thrust. If the jets are asymmetric, the thrust changes the trajectory in measurable ways. The preliminary orbit solution shows an anomaly, a tiny acceleration. Just arrow points, 3 millimeters per second squared, perpendicular to the sun direction. That's small, barely above the detection threshold, but it's there. Non-gravitational acceleration is normal for comets. Asymmetric outgassing from the day-side hemisphere pushes the nucleus in the sun-ward direction. You see it all the time. But 3I Atlas's acceleration is perpendicular, not sun-ward. That's weird. It could be a rotation effect. If the jets fire preferentially when they're oriented in a specific direction relative to the nucleus spin axis, the thrust averages out to a net acceleration perpendicular to the sun. Or it could be deliberate course correction, adjusting the trajectory to maintain optimal geometry. We need more data. Another week of astrometry would nail it down. But we don't have another week. The object is fading. By February, it'll be too faint for precise position measurements. So we're left with uncertainty. A tantalizing hint that might be signal or might be noise. This is what the week tells us: the data is consistent with both natural and artificial explanations. The opposition surge points toward processed grains. The spectroscopy points toward natural dust sheet geometry. The trajectory points toward, we don't know yet. Every answer raises new questions. And in a few days, the object will be gone, and the questions will remain. Let me bring this back to the beginning. On January 22, 2026 at 2:37 p.m. Universal Time, 3I Atlas reached a phase angle of 0.16 degrees. For 1 week we had a window. A unique observational opportunity. A chance to examine an interstellar visitor with forensic precision. We collected the data. We ran the tests. We built the models. And now we have to decide what we saw. Either 3I Atlas is a natural object, a comet with unusual properties, but explicable through known physics that happened to align with Earth and Sun at the perfect moment for observation. Or the alignment wasn't a coincidence. If it's natural, we've learned something profound about the diversity of interstellar objects, about the chemistry of other star systems, about the survival of volatiles during million-year journeys through the void. If it's not natural, we've learned something even more profound: we're not alone. And someone is watching. The data doesn't force a conclusion. Not yet. Maybe not ever. But it forces a question. And the question is enough to change everything. There's a moment in every detective story when the case closes, and you realize the mystery was never about the facts. It was about what the facts mean. 3I Atlas will leave our solar system. The data will be archived. The papers will be published. Some will argue for natural explanations. Others will point to anomalies that don't quite fit. The debate will continue in journals and conferences and late-night conversations in observatory control rooms. But something has shifted. For most of human history, we looked at the universe as a spectacle, a backdrop, something to observe, catalog, measure, but never something that observes us in return. The stars were distant and indifferent. Space was empty. We were alone in our corner of the galaxy, shouting into the void with no expectation of answer. And then we started finding things. Oumuanua Borisov. Now 3I Atlas, objects from other star systems, carrying the chemistry and history of worlds we'll never visit. Visitors. Messengers, even if they carry no message we can read. With each discovery, the universe becomes a little less empty, a little more populated, a little more like a place where things happens. Not just stars burning and planets orbiting, but trajectories intersecting, coincidences occurring, patterns emerging. And patterns demand interpretation. When you see a pattern, your brain tries to explain it. That's what brains do. They find order in chaos, meaning in randomness, intention in accident. It's a survival trait. The ancestors who saw patterns in predator behavior lived longer than the ones who assumed everything was random. But that same trait makes us vulnerable. We see faces in clouds, constellations in star fields, messages and noise. So when we look at 3I Atlas and see symmetric jets, timed outbursts, aligned geometry, we have to ask, is this a pattern, or are we forcing a pattern onto data that doesn't really contain one? The scientific method is supposed to protect us from this mistake. Testable hypotheses, repeatable experiments, peer review, skepticism is a virtue. But science operates on incomplete information. We can't rerun the universe. We can't summon another 3I Atlas to test our theories. We get one shot. One data set, one moment to decide whether what we're seeing is extraordinary or ordinary. And the decision we make changes who we are. Let me tell you what happens if 3I Atlas is natural. We catalog it, add it to the database of interstellar objects. Compare it to Oumuanua and Borisov. Note the differences. Update our models of how comets form in other star systems. We publish papers. Lots of papers. Opposition surge in the interstellar comet 3I Atlas. Evidence for compact grains. Symmetric jet morphology in 3I Atlas. Say natural consequence of trimodal fracture geometry. Non-gravitational acceleration in 3I Atlas. Torque from asymmetric outgassing. The papers explain everything. Each anomaly is resolved. The dust is compact because of thermal processing in the birth system. The jets are symmetric because of lucky geology. The timing is coincidence. The mystery dissolves into mundane physics, and we move on. We wait for the next interstellar visitor, hope it arrives when our telescopes are ready, when the geometry is favorable, when we have the resources to observe it properly. Maybe in 5 years. Maybe in 50. Maybe in 50. Maybe never. Interstellar objects are rare. We've detected 3 in the modern era. There could be thousands passing through the solar system annually, but most are too small or too faint or on trajectories that don't bring them close enough to notice. We keep searching. We keep cataloging. We build better instruments, launch more surveys, automate the discovery process so we catch these visitors sooner, track them longer, extract more data before they vanish. And slowly, over decades, we assemble a picture of what's out there. The diversity of planetary systems, the range of compositions, the frequencies of different formation environments. It's good science, important work, the kind of incremental progress that builds knowledge, layer by layer, year by year. But it doesn't change anything fundamental. The universe remains a place we observe. We're still alone in it, cataloging its contents like naturalists in a forest, naming species, mapping ecosystems, understanding mechanisms. We're the subjects, the universe is the object. Now let me tell you what happens if 3I Atlas is not natural. Everything changes. Not immediately. Not obviously. The headlines fade, the public gets bored. Governments classify the data or release it with caveats. Scientists argue. Dick Nukers debunk. Believers believe. But underneath, quietly, a shift occurs. We stop being the only observers. We become the observed. That changes the questions we ask. Instead of what is the universe made of, we ask who else is looking. Instead of how did life begin on Earth, we ask how many times has life begun. Instead of are we alone, we ask why haven't they contacted us openly. The Fermi paradox stops being a paradox and starts being a constraint. If they're here, watching, but not revealing themselves, that tells us something about their intentions, or their ethics, or the rules of cosmic engagement. Maybe first contact is always ambiguous. Maybe advanced civilizations have learned that revealing themselves too directly causes damage, cultural contamination, technological disruption, existential panic. So they leave clues, patterns, objects that could be natural or could be designed, depending on how hard you look. They give us the choice. Interpret this as you will. Believe or don't believe. Either wave, you've been seen. That's the zoo hypothesis. The idea that Earth is being observed by extraterrestrial intelligence that deliberately avoids contact to prevent interference with our natural development. It's unfalsifiable, which makes it unscientific, but unfalsifiable doesn't mean false. And if it's true, then 3i Atlas isn't a comet. It's a message. Not a message in language or mathematics, those are too explicit, too undeniable. A message in ambiguity, a test. Do you notice? Do you wonder? Do you have the intellectual courage to consider possibilities that challenge your worldview? This is the gauntlet thrown down, and how we respond, whether we dismiss it, investigate it, or embrace it, reveals who we are as a species. Here's the thing about being observed. It makes you self-minus conscious. For billion years life on Earth evolved in isolation. No audience, no judges, no cosmic context for our existence. We could be special or ordinary, and there was no way to know. But if we're being watched, if 3i Atlas is evidence that someone out there is paying attention, then suddenly we have context. We're not alone. We're part of a larger community, whether we know it or not. And that changes how we see ourselves. Are we primitive? Advanced? Interesting? Dangerous? Do they see us as children playing with fire, or as peers worthy of contact? We don't know, we can't know, unless they tell us. And maybe they never will. But the possibility is enough. The possibility reframes everything. When we launch space probes, are we sending ambassadors or trash? When we broadcast radio signals, are we announcing our presence or spamming the cosmos? When we develop artificial intelligence, are we taking a step toward joining the galactic community or disqualifying ourselves from it? The questions sound absurd when you say them out loud. Paranoid, self-aggrandizing. As if the universe cares what we do on our tiny rock orbiting an average star. But if 3i Atlas is artificial, the universe does care. Someone cares, and that makes our choices matter in ways we never imagined. Let me bring this to the philosophical edge. The universe is not a book waiting to be read. It's not a static collection of facts that we slowly uncover through observation and experiment. The universe is a process, a conversation, an exchange between matter and energy, between structure and entropy, between structure and entropy, between randomness and order, and now, maybe, between us and them. If we're being observed, we're part of that conversation. Our actions, what we build, what we discover, how we treat each other, are being noted, evaluated, remembered. That's terrifying. It means we're accountable, not to gods or moral absolutes, but to whatever intelligence might be out there watching, waiting to see if we're worth engaging. But it's also exhilarating. It means we matter. Not cosmically worst ill dust on a grain of sand in an infinite desert, but contextually. Within the framework of intelligent life in the universe, we're a data point, a variable, a participant. And participation means agency. We get to choose how this story goes. Do we continue fighting over resources, borders, ideologies? Do we poison our planet and squander our potential? Or do we grow up, unify? Reach outward with curiosity and humility, ready to join whatever community exists out there, if it exists at all. The choice is ours. It always has been. But now, maybe, someone is watching to see what we choose. The universe is no longer a dead expanse of matter following deterministic laws, playing out across billions of years with no witnesses and no meaning. It's a stage, and we're on it. The universe is no longer a void into which we shout, hoping for echoes that never come. It's a network, and we're nodes in it, connected by light and gravity and maybe, just maybe, by intention. The universe is no longer indifferent to our existence, our struggles, our triumphs. It's watching, waiting, wondering what we'll do next. And in 7 days, when 3I Atlas crosses Jupiter's orbit and fades into the infrared, when the data stops flowing and the telescopes turn to other targets, we'll be left with a choice. We can decide it was natural, a comet, a coincidence, a reminder that the universe is vast and strange and full of things we don't yet understand, but nothing that fundamentally challenges our place in it. Or we can decide it was a message, a signal, a test. And if it was a test, we passed, we noticed, we wondered, we looked as carefully as our instruments allowed. We saw the pattern, even if we couldn't prove it. And somewhere, to 0.87 astronomical units away, accelerating outward at 57.7 kilometers per second, something that might be a comet and might be a probe continues its journey. Indifferent to our debates, unconcerned with our conclusions, carrying its secrets back into the dark, leaving us changed whether we admit it or not. This is the story of 3I Atlas, an interstellar visitor that aligned itself with Earth and Sun at a moment when we were capable of observing it with unprecedented precision. An object that behaved just strangely enough to make us wonder, just subtly enough to deny certainty. We don't know what it is, we might never know. But we looked, we measured, we questioned. And in questioning, we became a little less alone. The universe is no longer a museum we wander through admiring exhibits. It's a conversation, and we're learning to listen.